We could monitor protein purification by electrophoresis, and we often will. If our protein has a particular biochemical function that we can measure, there's a better way. And that's by measuring something called the specific activity. Now, in order to measure specific activity, there are two things that we absolutely have to have. Okay? So in order to measure specific activity and monitor how this gets better as we purify our protein, the two things that we absolutely need to know are the activity, and I'll talk about what that is in a moment. And the second thing we need to know is the total amount of protein that we have at each step in our purification. Now, what do I mean by activity? Well, it's some measure of a chemical reaction that involves the protein function. Activity. This has to involve the protein's function. And we can define this in a whole bunch of different ways. How many people here have ever in their life used, for example, a restriction enzyme to cut a piece of DNA? Okay, so one that you probably are familiar with is this one called EcoR1. Comes from E. coli. It was one of the first restriction enzymes ever found. That's where the name comes from. E. coli, restriction enzyme 1. And when you buy it, it comes in a tube. And this tube has 10,000 units of EcoR1, and that unit tells us what the activity is. 1 unit is defined as the amount of enzyme required to cut a microgram of phage lambda DNA in 1 hour at 37 degrees in a reaction volume of 50 microliters. So that's an example of what we mean by the activity. Now, if we know the activity, right, and we're going to measure this activity in units. And the units will be different depending on what the protein does, but I've given you an example of one type of units. Now, how do I measure the protein concentration? There are a couple different ways that I can measure concentration. One way that I might choose to do it, right, total amount of protein. So I need to know protein concentration. And you know one way that I could do this right away, right? I could just measure the absorbance. Say at 280 nanomolar. Sorry, nanometers. Because we went through this already. If I plot the absorption as a function of wavelength, you know from the last lecture that I get an absorbance here that's either 280 or 276 nanometers, depending on whether or not I'm talking about tryptophan or tyrosine. We went through this the last time. And therefore, we said that the absorption of any solution was equal to epsilon times the concentration times L. L was the path length, epsilon was the extinction coefficient for the protein, and you would agree that the extinction coefficient for the protein was going to be, it would be some function, some sum, right, of the number of tryptophan residues and tyrosine residues that were in the protein. Okay? That makes sense. Nothing fancy there. Okay? Now, there's a problem, though, if I try to do that, and that will work really well once I have my protein semi-purified. But at the beginning, when I've just lysed my cells, there's a lot of DNA and RNA there, and they're going to absorb at 260 nanometers, and that's going to make it really complicated. And so clearly, although this is a great way later on, it's not such a good technique at the beginning. So I need some other techniques. And so some other techniques include dye binding assays.